I think it'll be nice once they're done. I think this projector is already better than the old one. I'm looking forward to seeing what it's like when it's done, but you're all sitting in a good spot. So, okay, so before we start, I want to point out a few things on the schedule. We're starting kind of a new general section of class today on like things involving regression, and I'm using this term fairly broadly. I'll talk about that soon. There are some various things coming up just to be aware of. The clustering homework is due on Wednesday, so make sure that you finish that and turn that in. I think most of you are doing pretty well in there already from what I've talked to. Okay, so a week from today is going to be the first midterm. It's going to be here in the classroom. Everyone needs to be here for that. So this is not one of those days you can take the midterm over the video. That's not going to work. So you all have to be here. So I expect that if you know it backwards and forwards, maybe you can finish in like if I were taking it, I bet I could finish in 10 or 15 minutes. But most people will take most of the class period. So expect to be here for most of the class. And that's nothing wrong with that. Double checking all that stuff. So but it's going to be closed computer, so you can't have any sort of electronic devices. Okay, I don't want that just keeps cheating out of it fairly well. But you can bring in whatever you want printed on paper. So if you want to print out all my notes, you can. It's a lot. I feel bad about all the trees, but I don't know a better way to keep otherwise you can't monitor what you're doing on your laptops and such. No, you should not need a calculator either. So you won't need to do any real calculations. If you have to add something and you don't trust your addition, then write out the word. And if you add it wrong, then it's not going to be marked wrong as long as you set the right thing. But you shouldn't need a calculator even. No calculators are allowed. Okay. So that's and it's going to cover everything up through the clustering part of the class. So through the spectral clustering will be the last lecture covered. Okay? So I timed it so the clustering homework is due Wednesday, and so you'll get to do all of the you'll get to practice doing everything on the homeworks. If you followed and did everything well in the homeworks, then you should be understood all those, should be in good shape on the midterm. There was some delays I had to do to check over things and releasing the grades for the document hash homework, but those should be out later today if they aren't already. Yeah, so it should be on those parts of the class. Okay, you should be able to do it all in here. You probably shouldn't need the notes, but you're welcome to have them just to check. Yeah.
So you say it's up through clustering? That's
correct. Through clustering. We'll not. I thought of including the streaming, but I decided not to do that because, I haven't released the homework on that, and I think I'd just rather you have a chance to work it out with the homework first. So that would potentially go into the end-term test, which again will only be on half the semester. Okay, and then after that we get spring break. There'll be a break, yay, or like I'll be sad not to see all of you. So I heard some of you chuckling too, so that's okay. Everyone needs a little bit of a break. So I have not updated the notes for this part of the semester yet from last year's notes. I usually update them probably 5 or 10% of the material. So I will get to these over spring break hopefully. And then on Monday after spring break, the intermediate report is going to be due. And half of this class, we're going to have half of the lecture, and then in the class we're going to, I'm going to pair you up with a couple of other groups, and you're going to give each other feedback on your project so far. And then you'll still turn them in, and I'll still give you feedback as well. But I think this way you'll get a much better sense of what other people are doing. So I hope you can all come to class that day as well. If not, let me know. I'll try and make some allowances on that day. But the midterm, you have to be here. And then, so this frequent items on the streaming part class will be due the following Wednesday. So I've loaded up stuff right after break. I'm sorry, but this homework is going to be half the length of the other homeworks. The graphs and the frequent and the streaming ones are going to be half the length of the other ones. So they shouldn't take us long. So that's compliments. Oh yeah, one more thing. I'm on Wednesday. I can't make my office hours, so I'm going to move them, I think, to Tuesday from 2:30 to 3:30, and then Michael has more 3:30 to 4:30, I think, on Tuesday also. So Michael's will be this time tomorrow, 3:30 to 2:30. I put mine right before here. If that's a problem, please let me know. I can try and make time elsewhere, but I'll try and be on Canvas and answer questions as well. All right, so that's update on the schedule. Okay. Good. So let's start talking about linear regression. So hopefully most of you have seen linear least squares regression before in a linear algebra course. So we're going to review it quickly and then tell you what its limitations are. And I'll start giving an overview of kind of the rest of this kind of part of the class, this series of lectures, what sort of other things we'll be covering. Okay, but I'm defining this regression in a way that's fairly broad, in that so you kind of want to define some. So we start. So the input is going to be some data at X, and then what we want to find is a simple pattern. Okay, we're going to call this pattern, let's call it L. Okay, and so we're going to think of a way of mapping from all of the data onto L. So in fact, you can think of some value L of X for all. So for all the data points, you should be able to think of, there's some value L of X, which represents that data point. Is usually the closest data point that fits the pattern. Okay, and so the simplest example of this is going to be, we're going to have some data, okay? And everyone can see those dots, okay? And then, so this data is going to be X, and then the line, and then the pattern L is going to be this line. And so then you're going to kind of map each data point onto here. So this is some data point X, and this is L of X. That green doesn't work very well, huh? It's a really dark green on here. I wonder if my connection is bad. So no green this lecture. No? All right. No green. Let me try again. Okay, so let's try orange. Yes. Okay. That's no. All right. Let's try black. Okay. Good. Good. And then, so this will be x, and this guy will be L of x. Okay. Good. Right. So we're going to map every data point. You can map each of the data points onto the pattern. Okay, and so then the idea of a regression is you're finding some simple pattern, and you can think of every data point as following that pattern. And you want the pattern not to be too far from the data in some sense. Okay, so this is kind of very general. I haven't defined anything, specific. But when you start defining things, you're making these modeling choices other than kind of these general rules I'm saying. And so often it will turn out that it makes a lot of sense to use something that's linear as the pattern. There are these nonlinear techniques which we'll talk about briefly, but you convert them into a linear technique. Or if you're in really high dimensions, often if you're trying to find some nonlinear structure, usually there's a slightly larger dimensional structure that's linear that works just as well. So we'll mainly be talking about these linear patterns in this case. One thing you should note before we move on, and this is all I'll say about it, you could also think of your data looking like this, right? And so in this case, you want to use a different pattern. You then want your pattern to be, so L, now in this case, is going to be these 3 data points. And these are going to be the centers for this assignment-based cluster. And then the mapping is just mapping every data point onto the closest center. This fits the same pattern. So this assignment-based clustering would be an example of this. And it turns out that when you're dealing with these at very large scale, the same techniques will work as well for dealing with things like the k-means clustering problem as they are going to work for the linear least squares regression. So there's actually a very kind of like a deep connection. Okay. So let's start defining our problem more precisely here. So linear least squares regression. So this is often called ordinary least squares. So we'll talk about this, and we'll mainly keep today's lecture for the data points, and I'll switch the data is now going to be a point set P, because we'll use X and Y for other stuff. So this will be a point set P, and we'll mainly try and talk about data that lives in R2. So in 2-dimensional data, just to keep all this big picture stuff kind of a little bit simpler, we'll talk about higher dimensional data in most of the rest of the lectures. And so now, for every data point P, I can say there's a X coordinate and a Y coordinate. So this is for every data point. Okay? So and so it may be useful to say that Px is going to be such that P and P and Py is just the Y coordinates. Okay, so it'll be easier to define based on these X and Y coordinates. Okay, and so now our goal is going to be a line L is defined by Y equals AX plus B. Okay, so this is an equation, right? So for every X coordinate, it defines a Y coordinate based on 2 parameters, A and B. Oh, red. Oh yeah, red's a color. Okay, so we need to find. These are the parameters. Okay, so we want to find these parameters, and so what we want to do is define a cost and we'll call this the L2 cost. It's defined as for a point set A, B is going to be Py minus okay, so basically I'm looking at the y coordinate that I want to predict, and this is my prediction based on the line, based on A and B, and I'm taking that difference in the y coordinate and I'm summing it, squaring it, and I'm summing these things up. So if I look at some data here, and I draw a line through here, then the errors, I'm looking at all of these differences in the y coordinate from what I'm predicting here. Okay? Great. Okay. Hopefully that will, okay, good. Right, it's the sum. I take all these distances here. This is called, if this is a point P, then this is R of P. This is called the residual, right? So it's the residual from the data to the line, and I'm squaring all those residual distances, right? This is basically L of Px, right? So that's I'm fitting the model there, and I'm looking at all those distances and squaring them. Okay. Yep.
Why do you use the vertical distance instead of the normal distance?
Yeah, good. This is a great question. So we will look at using the normal distance later. That will be called, in 2D, that's going to be the basically doing the principal component analysis. Okay? And it turns out that using the vertical distance is going to be really useful in that it's really saying we're trying to understand this y coordinate. And so when we go to higher dimensions, you're going to get more x coordinates, but often no more y coordinates. And the beauty of this is that the units that you use for each of your coordinates now don't matter anymore, because you translate everything into the effect on just the y coordinate. So the x coordinate units don't matter, they go into the coefficients. You're going to have more coefficients A in this case, A1, A2, A3, and so forth. And those are going to go into the coefficients, so you're going to solve for them. So it's not going to matter. Yeah.
And as far as using the L2 distance, besides, I mean, you could just like do the absolute value and not square, right?
Right. Yes.
That's just a modeling choice. Of, like,
that's a modeling choice, but as we'll see, this one is very nice to solve. You can solve this one exactly. Doing the L1 distance, you can set up some linear program and solve it. But you can't, this one is a closed form solution. Kind of like with the k-means clustering formulation, there's this, you can, every step, you use Rank-Lloyd's algorithm, you can take the mean of all the data points, and that gives you the best clustering. As hopefully you're finding out on the homework for question 3, asks you to look at the k-median cost, and that's summing the distances, and there's no closed form solution anymore. So you have to do something else, right? So again, this squared is going to give us a computational advantage. It's going to be very simple to do. Yeah. So we'll talk about these more, but these are great points as well. Okay. Yeah. So yeah, those were the next 2 points in my notes. Okay. Great. All right. So how do we solve this problem? How do we solve for A and B? It turns out that the first kind of highlight towards this is, if you look at this value, it's useless. Oh, okay. So if you look at this value here, this is going to be the mean point, and I'll write this as px bar, py bar. And so this is, for instance, let's say I've got right? So I'm taking the sum over all the x coordinates, and I'm averaging them. That gives me the mean. This line is going to go through the mean. Okay? So you can define this py similarly using the summing over the y coordinates as well. And so then what we're going to do is I'll write out the solution, and then we'll kind of try and stare at it a little bit and interpret what's going on. So the covariance of two point sets is going to be 1 over n. Okay, so I'm looking at this. Essentially, this should look kind of like a dot product after I've centered the data. This is not some crazy European accent. There's a bar. Okay. And so then you can also say that just the variance of px equals the covariance of px. Right? Okay? So this is going to be the variance of the x coordinates. And so it turns out that I can solve for A as the covariance of px, py divided by the variance of px. Okay? Which I can also think of as the dot product over the norm. Okay, so I'm going through this center point here, and then I'm taking the dot product between the x coordinates and the y coordinates, and that's kind of giving me the slope. So the A is telling me the rate at which I can change the x coordinate, and that increases the y coordinate. And then you need to also solve the intercept. This one is kind of a matter of units. This is py bar minus a px bar. Okay, so this one is easier. If I were to draw some x and y coordinates here, that didn't come through. Okay, let me try that different color. Nope. Right, so this is going to be x equals 0, and this is y equals to 0. Right, and so now this is the value of b, this distance. So it's the intercept here. You've probably all seen the slope intercept kind of interpretation before. And then a is kind of the rate of growth. So it's kind of like the angle. When you're doing angles, you think dot products. Okay, so there's this nice closed form solution for solving for A and B, which makes the least squares formulation very nice to work with. And so this was, I don't know, I've heard I think this was discovered by Gauss or something, but he didn't publish it. But then, this was discovered a long time ago, and people used this just because they could calculate it. Back when we didn't have computers, we had to work these out by hand. And you couldn't really set up a linear program, but you could work out these calculations. It's just a sum of all these things after you subtract out the mean. Right? Okay. So hopefully many of you have seen this before. Any questions on how you would do this? I'll talk a little bit about the multidimensional extensions next. Yeah.
Can you explain the dot product between px and y, or px and py?
Yeah, so is that,
What's, I mean, I know what an outmark is, but like, I don't understand, like, because there's a bunch of points, px.
yeah, let me, now I'm worried about, did something wrong, because it's, you need to center the data points. So this is, let me make a note here. This is after doing the centering. So, and the centering is what's being done here. You're subtracting out the mean. Okay, so now the dot product is defined between two vectors. And the dot product is simply the sum over all the coordinates and the product of the two coordinates. And that's what's going on here. That may be after center. I need to, I'll double check. Because, yeah, and so the variance, yeah, I was worried about this one over n term here. Yeah, this is on the covariance and the variance, so it gets canceled out. Right, and so the norm of a point is actually just the dot product with itself, or the squared norm of a point. Right, so that's the same thing. So that's what the variance is. And so those are defined with respect to the center. Is that, so it's kind of, it's, so again, the simple rule which is kind of useful is that you have two vectors, v and u, and so their dot product is equal to the norm of v, the norm of u times the cosine of the angle between them. If you have two vectors, u and v, and this is your angle. So it's, anytime you do something where it looks like you're doing something like an angle or a slope, you probably involves the dot product from somewhere. Okay. All right. So let's just review. One of the other nice things about this is it generalizes really well. This is all I'll say today about higher dimensions. Is that if you have a point set which actually lies in RD instead, then so then you can think of so you're going to break this point set into two parts. So X is going to be an n by d matrix. Okay, and so each row of X. So each row of X this will be my matrix X. Each row here is going to essentially be one of these data points. So the P. So I'm gonna, let's see. Let me write this as I'm going to have some data point P, and I'll write the coordinates a little bit differently now as R1, R2, R3, up to RD minus 1, RD. Okay, and so now what's going to happen is this part is going to be going to X, and this part is going to be the Y coordinate that we're trying to predict. Okay, so now when I write this coordinate in this matrix, I'm going to get R1, R2, R3, up to RD minus 1, and then the last row is going to be all ones. Or this last column. Okay, so I'm going to have n things here. I'm going to have n points in the matrix, and it's still going to be d columns. Okay, and now this last data point I'm going to treat specially. Okay, so the last data point is going to be py. I'm going to encapsulate everything from here, all these y coordinates into this vector py. Okay, and so now what I want to do is I want to find a vector A where this is going to approximately equal to Py. Right, so this is this linear equation. Okay, and so I've and so then if you want to solve this for all of the coordinates A, you can just say A is equal to X transpose X inverse X transpose Py. Okay, so this is going to look like this thing where this part up top here, this is going to look like the Px, Py, and this is going to look like this part here. It looks like 1 over the norm of x squared, or Px squared. Okay, so the first part is serving, it's got the inverse, that's like 1 over. It's serving the 1 over the magnitude of x, and the second part is like this dot product. Okay, and this solves, just doing this, solves for these optimal A coordinates, which are again minimizing the sum of these vertical distances to y. Okay, so if I were able to draw this in higher dimensions now, right, imagine these points are actually in 3D, then what I'm going to get for my surface for my solution, this is now L, which is described exactly by these A coordinates here. This is now a surface in here. So that this is going to be a d-1 dimensional surface. And I'm predicting the difference just in the y coordinate from all the data points onto this surface here. Okay? So it's always d-1 dimension. Okay. And so what happened to the b coordinate? Well, this b value ends up being this last coordinate here. Because I'm adding that to every data point. This is the offset, and basically I'm multiplying that b times the 1. Right? The b gets multiplied, this vector, this gets multiplied by this column, which is all 1, which is added on to everything. Okay, so this formulation allows you to write this as a linear algebra problem, which solves it in higher dimensions as well. Okay, and there's this useful thing sometimes useful called the hat matrix, which is x transpose x minus 1 x transpose. So this is the hat matrix. Because if you were to, you can make your predicted values of y, this is equal to xa, right? So if I take this matrix x, I multiply it by this vector of coefficients a, then those are my predicted values, which are supposed to look like are supposed to look like the y values I expected. Okay, and so it's called the hat matrix because if you were to expand out what the definition of A was, then I basically, or if you write that Py is this vector y instead, or y equals Py, then this is putting the hat on y. It's approximating. Usually you put a hat on something that's your estimated value. Okay, so this is powerful because you can, again, extend it to these higher dimensional problems. One other cool thing before we start poking holes in this is that you can also extend this to some nonlinear problems. So So in fact, we'll just talk about so polynomial least squares. So let's say now that my data kind of, hopefully you've seen this in linear algebra, but just to review, your data looks like this, and instead of fitting a line, you want to fit something that instead looks like a parabola. So how can I do this? Well, now my goal, given this data, is going to be, so I'm going to fit a polynomial of degree t. So in this case here, t equals 2, so just a parabola. And so then my goal for L here, my simple rule that I'm fitting to is that y is equal to a 0 plus a 1x plus a 2x squared up to a tx to the t. Okay, and so this is equal to some t equals to 0, or I equals to 0 up to t of ai x to the I. Okay, so I want to magically solve this the same way again. Well, all I have to do is, instead of having data that said just had an x coordinate, what I do is I take my data point x, and then this was, and I turn this into this this vector of 1 px, px squared, px cubed, and so forth. Right, so I just turn it into the vector, and then I use this higher dimensional extension. Right, so every data point which is one-dimensional, now I turn this into t plus one-dimensional data point, and I'm great. So, and you can extend this if your data originally lies instead of in one dimension, in 2 dimensions. You look at all combinations of up to a power t, and you can do this same thing, right? So this is called, this is either called a lifting, because you're going from some lower dimensional up to a higher dimensional space, but it's linear, or it's called a linearization. Okay, this trick. And so this allows you to do these polynomial extensions. So again, this simple linear least squares has this closed form solution. It extends to higher dimensions. It extends to these polynomial fits. There are ways you can do this with more general similarity functions and kernels and ways like that. So it seems like everything is going great. In fact, there's what's called the Gauss Markov theorem, which says that if I use this solution, so that then the least squares solution, as I described above, is optimal. So it's minimizing the sum of the squared errors, as long as I require that my solution has 0 expected error. So it's 0 expected error. So that means that the expected value of L of x minus x equals 0, and all errors, these are, I wrote these as the residuals, RP, which was again P of x minus this model L of, this is P of Y minus L of P of X are not known to be correlated. So that means that, I mean, the second one is totally common. We just don't know that there's some relation that some data points are related to other data points. We don't assume anything about it. Okay, and then the first one is saying that the expected error is 0. So for every prediction I make, I expect the error to be 0, which seems like a right thing to do. And if I want to do that, then this is the optimal way to do it. This least squares solution, as I described above, is the optimal. It minimizes the sum of the squared errors. Okay, so, right, you know, this is the point where I ask you if we're done, if we can stop with regression at this point and say, okay, let's skip the next 4.5 lectures, right, and just stop here. Yeah, this sounds good. Yeah, there are plenty of places like in the linear algebra class, right? You stopped here, right? This was it. This was done. Problem solved. There are some issues that we already mentioned a little bit. One is the squared error. Okay, so there's this squared error problem. So there's a squared error. So we're minimizing the sum of the squared error. So this minimizes the variance. So what's suboptimal about this? You mentioned instead minimizing just the sum of the errors. Why would you want to do that instead?
Or resistant outliers?
Yeah, so this is not resistant to outliers. A single data point can cause this regression to change vastly. It seems like not a good property to have. It's not uncommon to have some crazy readings if you have very big data sets. You don't want your total prediction to be skewed by one data point. So if you minimize the sum of errors, or which is one approach called least absolute regression, but there's another approach we'll talk about that is also resistant to outliers, based on minimizing the breakdown point, which I'll define. Okay, so another thing mentioned was the So these, when we're measuring these error residuals, we're only looking at the vertical distance. We're only looking at the y-coordinate. And this has some really nice properties in that it means that you don't have to worry about the units anymore. And so when you're dealing with things that don't have units that are all the same, then this is great. But if they all do have the same unit, then this might seem kind of strange. It means I'm only predicting this last coordinate. What if I just wanted to find a model that fits all of my data? I don't want to divide it into the part assumed as input and the part I'm predicting, right? So if I want to instead have some data here, like this, and then I predict here such that my error is actually this perpendicular distance here. So I want to minimize the perpendicular distance. Okay, so this is related to principal component analysis, which we'll talk about as well. And this essentially minimizes this projected on distance. It's treating all coordinates equally in building the model. Okay, so that's it also doesn't restrict that it can also have that this prediction we'll call it rank K. So if you're in very high dimensional space, you may not want your model to be d minus 1 dimensions. You may want it to be, you have 1,000 dimensions, you want a 10-dimensional model. So you can get a 10-dimensional subspace instead of a 999-dimensional subspace. Right? So this will also work with PCA. Okay, so what else is potentially suboptimal here? You're sampling more points? Yeah, okay, so there's one issue. There's what if n is less than d? Is that the problem? That you have more coordinates than you have data points. It turns out then in this case, you can't quite do this. This problem becomes undefined. So we'll talk about compressed sensing here. And this will help address this problem. In order to deal with it, you have to make another assumption about your model. Otherwise, you can find a model that you can find essentially d minus 1 dimensional subspace that exactly hits all the data points. You end up overfitting. Not sure. So if n is too small, then this doesn't work. But you can use compressed sensing as one way we'll fix this. Okay. What else? Let's look at this assumption here. This seems like a very fairly reasonable assumption. I want to have 0 expected error. So for every data point, I expect that my expected prediction is exactly the expected error I get with my prediction is exactly 0.
I think you're prone to overfitting.
Yeah, so this is going to go into overfitting. This is kind of I can so we can add a bias into the solution. If I add a bias, I no longer get expected error 0. That's what having a bias means. Okay, so the sum of squared errors, it turns out that the sum of, I'm going to have some py minus squared. You can break this into 2 parts, the variance plus the bias. Okay, and so this solution, the least squares solution, minimizes the variance, assuming the bias is 0. Okay, but if my overall goal is to make this as small as possible, then I'm not restricted to having the bias equal 0. Turns out you can do better. You can do better if you make the bias non-zero. So if you allow a non-zero bias, it turns out you can make an even better prediction. And this has to do with overfitting. So this helps with overfitting. And so intuitively, if you understand Bayesian statistics at all, you're adding a prior in the bias. The prior in Bayesian statistics is your bias here. And you're going to bias towards things that have a small slope. Things with a very large slope are going to tend to be very susceptible to noise, to a few data points. So you want to bias to having a smaller slope. And this is going to allow you to have better prediction when you get new data points. And we'll demonstrate this. Okay. And then the final point is that this can be, there's a step in here, the X transpose X inverse. This can be expensive. This step in solving, it's a nice closed form solution, but you have to do this matrix inverse step. And this is often slow. When you have a lot of data points, this is going to be a slow process. So we want to avoid this, and so to do this, we're gonna go back to like these streaming techniques, and this will go towards some techniques for so some techniques that generally fall in the category of what's called matrix sketching, which will be approximating a really big matrix, which is a much smaller one, so then anything you want to do, like the matrix inverse and such, you can do much more efficiently. It also has some other nice properties that you'll learn about what's actually being preserved in this linear regression. So there's some more to that story as well, but it's kind of, you can think of it dealing with the scalability issues. Okay, so all of these issues we haven't really addressed yet. So the rest of this section will be dealing with these issues, moving beyond least squares regression. Okay? So least squares regression is cool, it's great, but you can often do a little bit better. All right. Okay, so to start off and let me talk about outliers. And so before I talk about fixing our one potential fix for the least squares regression with outliers, let's talk about just one way of dealing with them. And these are called robust, or I'm blanking on this other term, or what?
Least absolute deviation.
Yeah, so we're not going to talk about least absolute deviation. We're going to talk about a specifically type of robust estimator that's called a resistive estimator. And so this is based on this notion of the breakdown point of an estimator. And so to talk about this, let me just describe the problem in one dimension. Okay, so let's say I've got data points in one dimension, and I can think of two estimators. One is going to be the mean, which is, this is just the same thing as the average, right? And we took this average several points during the least squares regression. The other is, on most normal data, is going to give a similar result, is the median. And the median is, again, basically you sort all the data and you take the point that's in the middle of the sorted order. Okay, so half the points are on the left, half the points are on the right. Okay, so now what happens if I add in an outlier here? So if I add this outlier point, what's going to happen is that this mean plus outlier is going to get pulled out, often can get pulled outside of the regular place of your data. So it's going to get pulled out here. This one out, and if you move this outlier even further off, you had some weird measurement error, got this really abnormal value, then the mean can be way outside of your data, whereas the change in the median is going to be very small. It's going to change just by 1 point in the sorted order at most. Right? I've added 1 point to the end of the sorted order, so either I stay the same or I move over 1 point. So it's going to be much more resistive to these outliers. It's going to change much less. Okay, and so now this notion of the breakdown point, this is basically going to be the number, or essentially the fraction of points that I can move to essentially infinity, and the estimator does not move to infinity. So it doesn't move, I don't have moved my estimator very far. So, for instance, the breakdown point of the mean is going to essentially, in the limit, is like 1 over n, or in the limit as n goes to infinity is 0. So I can move essentially as very small, or just one data point out to infinity, and the mean breaks down. With the median, this is going to be 1/2. So if I can move half the data points to infinity, or n over 2 minus 1 data points, and the median does not go to infinity. So it's much more resistant to outliers. Okay, so often these resistive estimators are trying to do things that you can extend this to linear regression in a way that looks like it's taking the median instead of the mean. And so there are a couple of famous things. So one is called the Stegall Estimator, which is more well known. This one has it's a little bit easier to work with. This one has a breakdown point of 0.293. There's something called the Seagull Estimator, which has a breakdown point of 0.5. The Seagull Estimator so basically what it does is it the Thiel-Sen estimator is let's see, it's so it takes all of the points by x coordinates. So px, then it sorts this into px1 is less than or equal to px2 is less than or equal to px3 and so forth. And then it's going to calculate the slopes of all pairs Sij is going to be an estimation of the slope, which is going to be yi minus, so yj minus yi xj minus xi. Right? So for every 2 data points, so this is going to be data point pi and pj, and it's going to look at only the pairs next to each other in the sorted order. So for every pair here, it's going to estimate the slope parameter a here as equal to as this slope as I've defined down here. So it's going to look at the expected slope of these, and then the a it's going to return is going to be the median of all these Sij for the pairs which are next to each other in the sorted order. No, actually it's not the sorted order, sorry. It's all of them such that pxi is less than pxj. So for all pxi is less than pxj, I've run out of page here. Sorry about that. This is J. Okay, it's kind of on there. There's a page break in there. Sorry about that. So for all the ones, so it's in the sort of order, it looks at all the pairs where one is less than the other, and it calculates the slope and takes the median of all these. So this turns out is robust, these estimators, because I'm using the median in this place. And then similarly, B is going to be the median of all these yi's minus a xi. Okay, so I can calculate the median just of those as well. And so this is going to be robust outliers. Now there are a few other ways of doing this. The Seagull extension, which is a bit more involved. You can look at minimizing the L1 errors. It turns out this will also be fairly robust, these outliers. But there are a variety of ways you can model the problem differently. And it's going to be like more robust in these ways. One other way, which we'll talk about, is to use a type of regularization. And so these Thiel-Sen estimators and these breakdown point-based estimators, they often end up being kind of combinatorially a little bit trickier. This works in 2 dimensions because I can sort the x. I need to sort the x coordinates here. But these, I need to sort these coordinates. But often people don't want to mess with these things, and they use what's called a regularizer instead. The regularizer, and I'll define it in a second, does not have this strong guarantee you won't have outliers, but it's going to penalize your solution away from outliers in some sense. Okay, so it won't be as strong in the breakdown point sense, that I still could have a small number of really bad outliers affect me, but it reduces the likelihood of this. Okay, so there are 2 types of regression we'll talk about. Or there are 2 types of regularization that we'll talk about. The first one, which will be easier to work with, is called regularization. So the first one's called the Tikhonov regularization. This is sometimes called the ridge regression. So these are the same thing. Okay, so now I'm going to, and so for both of these, it'll be simpler just to assume, it'll make the math a little simpler, that px, the mean of both the x and the y coordinates is equal to 0. So assume that it's been centered already. And so if you want to run these, you may want to do a centering step first, where you calculate the mean and you subtract that from all the coordinates next one. Okay, so now this one has a different goal, which is going to be, I'll write L2A, L2S. Okay, L2S, which is going to be, now I'm going to write the cost function here. Now I don't need to calculate the b-intercept here, so this is what's going to help simplify it. I don't need the b coordinate in 2D. And we'll spend a lecture talking about these in higher dimensions. And so now this is the sum over all of my data points, py minus a px squared. This part's the same, but I'm going to add an extra term onto the cost function. Okay, so I'm going to add this extra term. This term here, this term is called the regularizer. And so I want to make this whole expression small. So if the coordinate A, the slope coordinate, is large, this is going to make this expression bigger, even if this expression is smaller. For large slopes, this term is going to make it bigger. And S tells me how much. How do I trade off the actual, the variance error versus the bias? All right, so this is the regularizer. And so this is adding a bias. And this part has to do with the variance. So before I assumed the bias was 0, so essentially I set S equal to 0. There's no, by default, there was no penalty for having a large slope. Now I have a penalty for having a large slope. Okay, so it turns out that, so this is going to shrink it towards a small slope. So you can think of a shrinkage estimator in some sense, although the original shrinkage estimators were doing something very different. Okay, so what's, so it turns out that there's an equivalence, so that there's an equivalent formulation and we'll call this L2T of PA. And so this will be useful in understanding how it works. Again, I'm going to have sum over all points P of PY minus A times PX squared. But I'm going to restrict that such that A squared is less than or equal to T. So I'm going to have a hard constraint now that the slope can't be too big. Let's say the square of the slope cannot be bigger than T now. And so it turns out, how do I see this equivalence? As S becomes smaller, T becomes bigger, right? If S is 0, T is effectively infinity. I don't have any constraint. If I want to find equivalence, as S becomes larger, I put more constraint on the slope, then there's an equivalent formulation with the smaller T. So as for S larger, then equivalently, then I have T is going to be smaller. And I can see this by, I can solve the above formulation for a fixed S, and then whatever the slope is, whatever A squared is, that's my T value. Right? And so if I increase S, I'm going to have a larger and larger slope up to a point. So there's this equivalent formulation, but this is kind of a hard constraint. Okay, so the other nice thing about this is that if I want to solve this for A, there's a very simple solution. So AS, my estimate for A is going to be this. So instead of, which is going to be equivalent in the matrix notation for higher dimensions, X transpose X plus S squares times the identity matrix. And when we get to the higher dimensional stuff, I'll walk through some of these meanings more. Okay, so there's a very simple solution again. I just add this S here in this denominator. I add an S to it. Basically, the problem was if these values got really small compared to these values, so my X, the variation in X was very small compared to very large Y values, this became very sensitive. And so you're adding a term here, a constant on the bottom, so you're not dividing by something close to 0. It's kind of one way to think about it. Right, so again, this is as simple as solving for regular least squares regression, as long as I know what this value S is here. One way to think about it, let me try and draw a picture here. And it's a little hard to draw because typically people, so if you see data, and I'll try and draw this data like this. So typically you have data like this. And if you draw an outlier, you know, if you think of data like this, and then there should be some good fit that goes through here, you think, where am I going to draw that line in this picture? I'm going to draw it down here. because it's easier to fit in like a square picture, right? Right. If I were to draw this inside of a textbook, I'd want it to fit nicely inside of a box, right? But outliers, you would think of being very far away from your data, and so such that they really bias the slope. And so really what you want to think of the outlier as being all the way up here as one of my data points. So my data point is all the way up there. And so what's going to happen is I'm going to get a different slope which is larger than it should be. In fact, it should be much higher off the page. I can't even draw it. Right? It's going to bias the slope to be larger, and so I want to bias, it's going to usually cause the slope to be larger, and so I want to make the slope back closer to 0. These are going to be more trustworthy if my slope is closer to 0. Right? If the best fit looks something like this, nope. Right, so if my slope instead looked like this dashed line here, then if I have some x and y coordinates, remember it's centered, so these should all be kind of going through the origin, then if I have an x coordinate here, it's going to predict something way up here. So if I change the x coordinate a small amount to x prime, the difference in the y value is very large, right? This difference in the y value becomes very large because my slope is large. So I don't want these instabilities. So you want to kind of bias towards these smaller slopes, and these Tikhonov regularization is doing this for me. Okay, so it turns out that, and this is kind of the contrapositive essentially to the Gauss-Markov theorem. I go back up here, right? This Gauss-Markov theorem. If I relax this assumption, this assumed that I have 0 expected error, I should be able to get a smaller sum of squared errors if I add in some bias here. If I add in some bias, if I relax this. So it turns out there exists some parameter, there exists some parameter S such that, I guess to be careful in describing this, if you generate new data from the same distribution as the old data, so if, let's see, so P was drawn from some distribution IID, and then I do a new data point Q from this same distribution, and I fit, there's A hat and A hat S, then the expected, so there's some parameters here, okay, then the expected error, and now it's the sum of squared errors, so I want to look at the expected error from QY minus AQS squared. This is going to be strictly larger, I guess, unless the data lies exactly on a line or something like that, then the expected error from QY minus AS hat. This is QS squared. Okay, so if I draw the data from the same distribution, I see a new data point, I'm trying to predict its value, you're going to get smaller expected error in the squared error sense using some estimator chosen with S. Okay, so this is kind of the base of this. There is some value S that does better than if you do it with an S assumed to be 0. You don't always know what that is, but you can actually figure this out using cross-validation. So how to choose S. This is going to use cross-validation. And we'll talk about this a little bit. Hopefully you've seen some cross-validation in the machine learning class. If you haven't taken that, we'll talk about this later in the semester, how you go about doing this. And I believe we'll probably set up a homework where you'll actually see this actually work in practice, where you'll have to choose an S that actually works better on the held out data. Okay, so hopefully this seems really cool if you haven't seen this before. It should be very cool that you can do this. You can do better by adding this bias towards a smaller slope. All right, let's see, I have 5 minutes left, and so I'll talk about principal component analysis. Basically, that'll be all of next lecture. We'll be talking about the singular value decomposition and how to interpret this, so linear algebra operation, and how to get the principal component analysis out of that. Basically, that's minimizing the sum of this orthogonal distance error. So I'll save that till next lecture. One more thing I want to talk about is this other form of regularization called the lasso. This is often called this is also called basis pursuit. And this is a very small difference. The goal now is a different cost function. It's again going to have this least squared term here. Right, so it's sum of squared errors, but plus S times A. So now I'm minimizing the absolute value of A, not the squared value. Okay, and so when we get to higher dimensions, you're going to have more than one coordinate coefficient you're trying to estimate. This is going to be an L1 norm instead of an L2 norm. Okay, and so there's again an equivalent formulation. L1T is going to be again the sum. These such that the absolute value of A now is less than T. Okay, so again, there's this formalization where I put a hard cap on T. Now, in one dimension, these are going to be, or in 2 dimensions, the data, these are going to be equivalent, because if I have a cap on the absolute value of T or on the squared size of T, I can change between different values of T, whether it's the lasso or it's the ridge regression, because of this equivalent formulation. I can set a different value T depending on whether I'm doing the ridge or I'm doing the lasso, and I'm going to get a similar thing, which means I can also set the same value S. So these really aren't different in 2D. These are the same thing in 2D. What's going to happen, though, in higher dimensions is going to be really interesting, and we'll spend a whole lecture on this, is that you often you're going to get, remember the higher dimensional version, this is going to be a vector of coordinates, of coefficients here. And one nice thing you might want is to say, what if I made a bunch of these coefficients 0? Meaning I didn't need those terms in my model, my simple model. I can make it simpler by saying some of the coordinates, I don't need those in order to make a prediction. If I set these coefficients to be 0, then then I say those are unimportant. And so when I do the lasso with higher dimensions, it turns out by having this regularizer, the L1 regularizer, instead of the squared distance, then it's going to kind of snap some of the coordinates to 0 when you solve this optimization. And so it's going to give you a sparse solution. So this is going to be something like feature selection. It tells you which coefficients are more important. It doesn't exactly tell you that, because sometimes there would be two coefficients and they both tell you essentially the same thing, so you can set one to 0 and the other one not to 0. And so it doesn't tell you this information. It could have set one or not the other, and it really doesn't make a difference. So feature selection has some kind of issues to it, but it's going to give you this nice sparsity. Okay, so we'll have a lecture talking about, we'll need to use the difference in the shape between the L1 norm and the L2 norm, and that's going to give you this sparsity property that's going to come out of here. However, the bad thing about this is that unlike ridge regression, there's not this nice closed form solution anymore. I can't just stick it inside of this matrix inverse. I can't just do this trick up here where I do this. I can no longer solve it simply. So I need to use more careful techniques to solve it. If I use just the ridge regression in higher dimensions, I'm not going to get non-zero coordinates though. I'm not going to get these 0 coefficients. I'm not going to get those. It's just going to make all the coefficients a little bit smaller, but not all the way to 0. So I'm kind of stuck in between these two things. It turns out there's still a reasonably good solution for solving the lasso. It's just not as simple. Okay, so that's it for today. We'll talk about the SVD and PCA on Wednesday. And don't forget the homework. And don't forget, I changed my office hours. Sorry about this again, to Tuesday, 2:30 to 3:30.